Okay, hello, welcome. We are going to talk today about some probability. Specifically, we're going to talk about independence versus disjoint events and the relationship between those two words and things. And then we're going to look at some tree diagrams. And we're going to use some tree diagrams to help us answer some probability questions. So here is a theory, a statement that is always going to be true. Two events cannot be both disjoint and independent. So we're going to explore this a little bit. So I want you to think for a second about what would a Venn diagram look like when events A and B are disjoint. So remember, disjoint is another word for mutually exclusive while you're thinking. So events A and B are disjoint, or events A and B are mutually exclusive. That means that they can't happen at the same time, right? If I pick an M&M out of a bag, it can't be red and blue. It has to be one or the other. So my Venn diagram would look like this. They wouldn't be overlapping. Now, when I think about independence, can these events be independent if this is what my Venn diagram looks like? So if the events are disjoint, can they also be independent? Remember what independence means. It means that knowing something about one thing doesn't have an impact on the probability that the other thing is going to occur. Well, here's the thing. According to this Venn diagram, if I know that A has occurred, could B occur? No. If I know that A has happened, the probability of B is 0. It couldn't have happened, right? So in other words, these events are not independent. So they are disjoint and they are not independent. So in other words, two events cannot be disjoint and independent. It's impossible. Let's explore this a little bit more. So we're going to talk about a deck of cards, and we're going to define a couple events here. We're going to use these to kind of explore this. So define events. A is picking a card randomly and the card is a king. B, picking a card randomly, the card's red. C, picking a card randomly, the card's an ace. Okay, so find the probability of A. So there's 52 cards in my deck of cards, right? And out of my 52 cards, there's 4 kings. Or in other words, 1 out of 13. Okay, find the probability of event B. So I have my hearts and I have my diamonds. Or in other words, I have 26 out of 52 cards, or 1/2 of the cards are red, right? And then the probability of event C, probability of event C, there's 4 aces out of the 52 cards, or in other words, the probability is 1 out of 13. So number 2, are events A and B disjoint? Disjoint or mutually exclusive? Why or why not? So in other words, can I have a card that is both A and B? Can I have a card that's both a king and red? Yeah, I can. So I have the king of hearts and the king of diamonds. That doesn't look good, but so therefore A and B are not disjoint or not mutually exclusive because I have 2 cards that are a king and red. In other words, think back to our formulas. The probability of A and B is going to be 2 out of 52. If 2 events are disjoint, the probability of A and B is 0. Right? So the answer is no. All right. Part 3. If you draw a king, find the probability of B. If I draw a king, find the probability of B. So in other words, find the probability of B given A, right? That's conditional. If you draw a king, we're conditioning on the card is A, it's a king. So my kings, I'm conditioning on the card being a king. So I have 4 kings, right? Now I want the probability that it's red. So I have 2 red kings and 2 black kings. So this would be 2 out of 4 or 1/2, right? Part B, so 3B, if you draw a red, find the probability of A. So drawing a red is B. So in other words, I'm finding the probability of A given that the card's red, or given B, right? So if the card is red, that's the part I'm conditioning on. The card's red. So remember, I have 26 reds, right? So I have 26 reds. Out of those 26 reds, what's the probability that I have a king? Well, 2 of those are going to be kings, right? So the probability of A given B is 2 out of 26, or in other words, 1 out of 13. Now, part C, what does this tell you about these events? Does knowing that a card is a king affect whether it's a red or not? So in other words, are these 2 events independent? Is the probability of B equal to the probability of B given A? So the probability of B was up here, it was 1/2. The probability of B given A is also 1/2. And then was the probability of A equal to the probability of A given B? So the probability of A, 1 over 13, is equal to the probability of A given B. Those are both true. And if I found the probability of A given B complement, and if I found the probability of B given A complement, they would also be equal. And so does knowing that a card is a king affect whether or not it's a red? The answer is no. So they are independent. Okay, so in other words, A and B are independent and not disjoint. So actually, I'm going to jump over here to number 6. In conclusion, A and B are independent and not disjoint. Okay, now let's look at A and C. Are A and C disjoint? Why or why not? So A and C, can you have a card that is a king and an ace at the same time? Remember, disjoint means can they happen at the same time? And remember, this is the same thing as mutually exclusive. Can I pick one card and it's a king and an ace at the same time? So the answer here is no, right? It's one or the other. It can't be both. So in other words, the probability of A and C, there aren't any of those cards. It's 0 out of 52, right? So are they disjoint? Yep. They are, because the probability of A and C is 0. So 5A, if you draw a king, find the probability of C. So in other words, what's the probability of C given that it's a king? So given A. So the given part is that it's a king, right? So if the given part is a king, there's 4 kings. What's the probability that it's an ace? Well, that's 0, right? There's no aces. So in other words, it's 0. Now let's look at the probability of, if you draw an ace, find the probability of A. So A given C. And in this case, remember, we're conditioning on a card being an ace. So there's 4 aces. There's 4 aces in the deck. Now, what's the probability that out of those 4 aces that you have a king? None of them, right? So what does this tell you about the events? Does knowing that a card is a king affect whether it's an ace or not? So in other words, I got to check, is the probability of C equal to the probability of C given A? Well, the probability of C, we said, was 1 out of 13, right? Is that equal to the probability of C given A? They are not. And the probability of A, is that the probability of A given C? The probability of A was 1 out of 13 as well. A given C is 0. So does knowing that a card is a king affect whether or not it's an ace? Yes. If I know that a card's a king, I know that it's definitely not an ace. So these are not independent, right? So in conclusion, A and B are independent and not disjoint. And A and C are not independent. Oh, D, E, P, sorry. Not independent, and yes, they are disjoint. So they have to be one or the other. They can't be both. They can be neither. They can be neither disjoint, but also not independent. But they can't be both. Okay, so next thing you need to know. If A and B are independent events, then A complement and B complement are also independent events. Let's look at this. So pick a card from a deck of cards. A is picking a king. B is picking a red. So king and red, kind of like what we did A and B before, right? So are they independent? So flipping back here one more time. Are they independent? Part C here, right here. What does this tell you about these events? We already proved that they are independent. Yes, we already proved it. So define A complement and B complement. So A complement would be picking something other than a king. So like a 2 through 10, a jack, a queen, or an ace. And B complement would be picking a black card, right? So the probability of A complement out of 52 cards, right? 4 out of the 52 are kings. So out of 52 cards, we would have 48 out of them. Or in other words, 12 out of 13 that are not a king. The probability of B complement, in other words, the probability that the card is a black, this would still be a half, right? A half of the cards are black, 26 out of 52. So let's think about if A complement and B complement are independent events. So remember, we're going to find some conditional probabilities. So we know the probability of A complement is 12 out of 13. Now we got to find the conditional probability. If they are independent, the probability of A complement has to be equal to the probability of A complement given B complement. Okay, so let's think this through. The probability of A complement given B complement. So it's the probability that you have a 2 through 10 jack, queen, or ace given that the card is black. So how many black cards are there? There's 26 black cards, right? And out of those 26 black cards, how many of them are a 2 through 10 jack, queen, or ace? Well, that's like 12 different options. And we have like the ace of spades and the ace of clubs, the queen of spades, the queen of clubs, right? So 24 out of these 26 cards are going to be not a king, or in other words, A complement. When I reduce that, that's 12 out of 13. Well, what was the probability of A complement? It was 12 out of 13. So yes, these two things are equal. So far, so good. Now we need the probability of B complement to be equal to the probability of B complement given A complement. So we already know the probability of B complement is a half. What's the probability of B complement given A complement? So A complement, I know this is getting like, it's a lot to wrap your mind around, right? A complement. So anything other than a king, right? That's all these cards. So we said there's actually going to be 52 total cards. Take out the 4 kings. So you have 48 cards that are not kings, right? That's the condition part. Now, out of those 48 cards, how many of them are black? Well, think about it. Half of them are red, half of them are black, right? Or I could think like, well, so I have a 2, 3, 4, 5, 6, 7, 8, 9, up through 10, jack, queen, and ace. But I have all of those in spades and also in clubs. So I have 24 out of 48. In other words, 1/2 equals 1/2. So are they independent? Yep, they are independent. So A complement and B complement are independent. Think about it. If I pick a card and I know it's red, does that affect the chances of the card being a king? If you kind of think through that, that should make sense, that it doesn't affect it. Alternatively, if I pick a card and it's a king, does that impact the chances that the card is red? Nope, there's still a 1/2 chance. So you need to be able to show this mathematically, kind of like what we just did here with our conditional probabilities. Okay, let's talk about some tree diagrams. So a tree diagram is going to show us a whole sample space when we have multiple stages, okay? But here's the key. We're going to list some probabilities on this tree diagram now, and we're going to talk about this in just a second as we go through, but the probabilities after the first stage are actually going to be conditional probabilities, believe it or not. So let's look. If we randomly choose a school day and note if Shannon hits the snooze button or not and whether she gets to her first class on time. So Shannon sets her alarm for school every day, right? Sometimes she hits the snooze button, sometimes she doesn't. And so what I'm telling you is that there's a 60% chance that she hits the snooze button and a 40% chance that she's like, oh, my alarm's going off, I'm getting right up, right? So now she's going to hit that snooze button and then she's going to school. Sometimes she's on time. So here I am here. Sometimes she's late, right? Now, given that she hits the snooze button, she's on time to school 70% of the time. That's a conditional probability. Given that she hits the snooze button, she's late 30% of the time. You're going to notice both of these are conditional, and they're both conditioning on the same thing, that she hits snooze. So they add up to 1. Because if I am under the condition that she hits snooze, there's only 2 options. She's either on time or she's late to school. And then down at the bottom of the tree diagram, if she doesn't hit snooze, again, she's either on time or she's late. She's on time 90% of the time, given that she didn't hit snooze. And given that she didn't hit snooze, she's late 10% of the time. So these are conditional probabilities that add up to 1, because given that she doesn't hit snooze, those are all the possible options that could happen. So these things, this and this, these are actually conditional probabilities. You may never have thought of that before. But I have 4 possible outcomes. So either she hits snooze and she's on time, she hits snooze and she's late, or she doesn't hit snooze and she's on time, doesn't hit snooze and she's late, right? Okay, let's look at how does this come into play. So recently, Harris Interactive reported that 20% of millennials, 25% of Gen Xers, 21% of baby boomers, and 17% of matures read more e-books than print books. So according to the U.S. Census Bureau, 34% of those 18 and over are millennials, 22% of are Gen Xers, 30% are baby boomers, and 14% are matures. Suppose we select one U.S. adult at random and record which generation the person is from and whether or not she reads more ebooks or print books. So you might be thinking, you might be feeling a little bit overwhelmed, but think about this. What is the variable that would come first in my tree diagram? So the variable that would come first was what generation the person is, right? And I can tell that because these probabilities here are not conditional. This is just out of the U.S. Census, right? It's saying, according to the U.S. Census, and it's just stating percentages. So these are not conditional, okay? Everything in yellow is not conditional, okay? But then if I go back to the beginning, it says Harrison Interactive reported that 20% of millennials read more ebooks than print books. 25% of Gen Xers read more ebooks than print books. So all of these that I'm going to highlight in pink, these are all conditioning on the generation. Okay, so those are all conditional probabilities. So this is what my tree diagram would look like. So we have a randomly chosen U.S. adult. There's a 34% chance that they're a millennial. Now, given that they're given that they are a millennial, there's a 20% chance that they read more ebooks. And that's directly from here, right? Now that means that given that they're a millennial, there's an 80% chance that they actually read more print books. So like this probability right here is the probability that someone reads more ebooks given that they're a millennial, right? And this is the probability that someone reads more print given that they're a millennial, right? And then hopefully you can go through and kind of decipher where the rest of this came from. So 25% of Gen Xers read more ebooks than print books. That's this number right here. 21% of the baby boomers. So here's the baby boomers. Here's that 21%. 17% of the matures read more ebooks, right? Okay, so there's my tree diagram. Now, what could I use this tree diagram to help me figure out? So here's a typical question that you would use a tree diagram for. Find the probability that the person reads more ebooks than print books. So, in other words, if I look at this question, it's not conditional. I don't care what generation they're from. I'm just saying, out of everyone, what's the probability that someone reads more ebooks than print books? So I can multiply these two probabilities because this is the probability that they read ebooks given that they're a millennial. So if I want the probability of reading ebooks and millennials, I can find that by multiplying the probability of being a millennial times the probability of reading more ebooks given that they're millennial. Remember that multiplication rule? So I'm multiplying 0.34 times 0.20, 0.22 times 0.25, 0.3 times 0.21, 0.4 times 0.17. So just these ebooks. So if I add all those up, I get 20.98, or in other words, close to 21% of all people read more ebooks than print books. That's out of everyone, out of the population. Part C, suppose that the chosen person reads more ebooks than print books. What's the probability that he or she is a millennial? So now we're conditioning on the fact that the person reads more ebooks. So we want the probability that they're a millennial given that they read more ebooks, right? Now think about your conditional probability formula. To figure this out, I need the probability that someone's a millennial and that they read more ebooks. And I can divide that by the given part. Okay? And so very similar from before, I'm going to take that 0.068. So in other words, millennial and reads more ebooks, multiply those two things together and get that here, divided by the given part. That given part was the number that we calculated in part B earlier. So that's where we get that 32%. So the probability that someone's a millennial, given that they read more ebooks than print books, is 32%. Okay, that was it. Hopefully that made sense. I do want to point out one thing before we wrap it up here. In this specific problem, you were in part A specifically told to make a tree diagram to help you answer these questions. And sometimes you might be told that, but I want you to start thinking about, if I'm just given a problem, I might not be told to draw the tree diagram. If I'm given a whole ton of information like this, some of it being conditional, and then I'm asked a question like this in part B, you need to say to yourself, oh, wait a minute. I have some probabilities and then I have some conditional probabilities. Maybe making a tree diagram might help me work this out. And this is just kind of like practice, practicing makes you better at anything, right? So the more you see problems like this, the more you'll kind of like get used to, when might I see a question where I use a tree diagram and when might I not use a tree diagram. And I'm not telling you that you would have to use a tree diagram. You can answer part B and you can answer part C without a tree diagram, but the tree diagram just makes it a lot easier. Okay, that's it. Thank you so much for watching. Have a great day.